the inverse. And towards the end of the most recent lesson, we looked at getting the inverse of a function. It used the determinant, and we had a method of getting an inverse function for inverse matrix for a 2 by 2 matrix. So let's take a look at a set of equations, two variables that we will solve using the inverse matrix. So let's take a look at the first visual. And we have the equations 5x plus 4y equals 12 and 3x minus 5y equals 22. Now, if you're one of these people that has a photographic memory, you should remember that you've seen this before. This was a system of equations we solved in Lesson 11 using the elimination method. We are now going to use the inverse method. Notice what we've done here at the bottom part of the visual. We've shown you these equations written as a matrix multiplication equation. That's a mouthful in any language. We have the first matrix, which contains the coefficients of the two equations, the x coefficients in column 1, the y coefficients in column 2. Then the next matrix is a 2 by 1, and that's called a column matrix. It only has one column, so it's a column matrix containing x and y. And then the column matrix on the other side of equals are the answer matrix. That's the numbers that are on the right side of equals in our equations. If you would use matrix multiplication to multiply the first matrix, the 5, 4, 3, negative 5, by the xy matrix and set it equal to the answers in the third matrix, the 12 and the 22, indeed you would get the two equations that are written at the top of the visual. Now, what I'd like to do is put this equation as in a matrix form on the board and see what we'll do to use the inverse matrix and then go back and actually solve them. So let's go to the board. Of course, it'd be a good idea to have our chalk. Very handy thing to have to write on the board. Okay. Again, what the visual showed you, we had this 5, 4, and we had the 3, negative 5, and then we had the xy, and we had the 12 and 22. Make sure we've copied this correctly. It's always a good idea when you write things down to ensure that you copy them correctly. Now, if this was simply an equation with one variable, what we would probably do is we divide the coefficient of the letter on both sides and we get x equals. But here we have matrices. And what we actually want to do is divide both sides by this matrix. We understand that we don't divide matrices. We multiply by the inverse. So what we really want to do is multiply this side of the equation by the inverse. We'll write that matrix out, inverse. And since we're multiplying from the left side of this matrix, we also, in effect, and I'll kind of show that with an arrow, we want to multiply this from the left. Remember, we saw that matrix multiplication is not commutative. It makes a difference which comes first. So we'd multiply, we'd stick that 5, 4, 3, negative 5 inverse matrix and multiply the 12, 22 matrix from the left. And when we've done that, we will be on our way to solving for x and y. The next visual actually shows us this same thing, but I did the visual because it shows you them all kind of lined up. We have the left side, we have the inverse times the original coefficient matrix times the xy matrix equals the inverse times what I call the answer matrix, the 12, 22 matrix. And remember, what happens when we multiply a matrix by its inverse? Let's go back to the board and talk about that. When I multiply this matrix by its inverse, it's no different than multiplying a number by its reciprocal. I am going to get the identity matrix, which we talked about in the previous chapter. So let me erase this, and we're going to multiply, and what we're going to get is the matrix 1, 0, 0, 1, the identity matrix. Now, what happens when we multiply the identity matrix times xy? When we multiply a number by 1, we get the same number. We multiply a matrix by the identity matrix, we get the same thing. It doesn't change anything, so we can erase this. And now what we have is XY matrix equals the product of the inverse times 12, 22. When we multiply this square matrix by this column matrix, we will get the answer. And in fact, what I would suggest that you do is stop the tape as soon as I stop talking and go ahead and multiply. First, find the inverse, and then multiply that inverse times this 1222 matrix. You should get a column matrix with two numbers in it. So go ahead and stop the tape now, go back and figure out how to get the inverse matrix for this, and then multiply that times the 1222 matrix. Okay, hopefully you've done that. If you haven't been able to do that, you probably need to go back to the previous lesson, lesson 26, and once again determine how to get the inverse and also determine how to multiply two matrices. All right, what are we going to do? Well, let's go ahead and go to the next visual. The next visual shows us how we got the inverse of that 5, 4, 3, negative 5 matrix. 1 over the determinant. The determinant is negative 37. And then, of course, we exchange the two numbers in the 1, 1 and 2, 2 position. So the negative 5 is now where the 5 was, and vice versa. And we change the signs of the other two numbers. The 4 becomes a negative 4. The negative 3, the 3 becomes a negative 3. And then we multiply through, and as indicated at the bottom of the visual, we have the inverse matrix. That is the 5/37, 4/37, 3/37, negative 5/37 is the inverse of our coefficient matrix. Looks kind of confusing, all those fractions in there. But in actuality, if you remember, when we solved this problem back in lesson 11, the answers were nice integers. So we shouldn't have any problem with fractions when we get all finished. But right now we have these fractions. Okay, let's take a look at the next visual. The next visual shows us what we just had on the board, that we have XY, which of course is now by itself on the left side, because when we multiplied the inverse matrix times the coefficient matrix, we got the identity matrix, and the identity matrix times the XY matrix gives us XY. On the right side of equals, we have the inverse matrix times that 1222, what I call the answer matrix. And when we multiply it, we get this column matrix shown in the second line, 148/37 and negative 74/37. Those fractions look kind of confusing, except that they immediately reduce to 4 and negative 2. So let's go back to the board, and let's replace this mess over here with the answer we got, which was 4 and negative 2. That was the column matrix we got when we multiplied the inverse times that 1222 matrix. If I have two matrices that are equal, they have the same number of rows, the same number of columns, they are equal, what does that mean? It means that each number here is the same as its corresponding number there, which means x equals 4 and y equals negative 2. And if you happen, by some strange circumstance, remember the answers to all the problems we've done, 4, negative 2 was the answer for xy in that problem we did in lesson 11. Obviously, we can go back and check in the original problem, and it will work. Now, right now, you may be saying, you know, I think I like the way you did it in lesson 11. It seemed a lot easier than this. That's because this is something new. Quite frankly, you need to do a few of these. You go back, and in fact, if your textbook has a lot of systems of two equations and two variables, go back and try doing some of these equations in your systems equation in your textbook using this method. And after you've done 4 or 5 or 6, I think you'll find it's a lot quicker and a lot easier. Okay? But then again, you may find, gee whiz, I keep making careless errors, and I'd much rather do it by elimination, the process we used in lesson 11. That's fine. Okay, now I want to go back and remind ourselves about determinants. Okay, do we remember what the determinant was? The determinant was a number that stood for a particular matrix. So let's go ahead and go to the next visual, which shows us we have two equations. AX plus BY equals C, and DX plus EY equals F. Now these two equations are a system of equations, two linear equations, two letters. The A, B, C, D, E, and F are just numbers. Okay, this is just like the problem we just did. And now we call the determinant of the coefficient matrix big D. And I apologize to any of you who live or are from Dallas. I know Dallas considers itself the big D, but I consider big D the determinant of the coefficient matrix. That is A, B, D, E, because A and B are the coefficients of X and Y in the first equation, and D and E are the coefficients of X and Y in the second equation. And this is going to be very important. When we get this determinant, it's going to help us solve systems of equations. In fact, the next visual will show us exactly how to do that. It starts off by saying we're using Cramer's rule. And correct, that's how Cramer spelled his name, with a C. Cramer was a mathematician who developed a method of using determinants to solve systems of equations. And to me, this is the best way. It's even better than the inverse method we just got through doing, because it is really slick. I mean, it works very quickly. And in fact, if you have a computer program or a graphing calculator that does determinants, this is so